video was like 45 minutes or whatever, but we can yeah, we can normalize it to 1. So what's going on? Chapter 9, sequences and series. So a quick rundown. So section 9.1 is introduction to sequences, and we're going to start a series after that. So a definition of a sequence, it's a function. That's all it is. Sequence is a function, domain of which is just a set of natural numbers. Okay, so 1, 2, 3, 4, and so forth. So that's a definition. Sequence is a function defined on a set of natural numbers. Doesn't have to be all natural numbers, just a set of natural numbers. So positive integers. So no fractions, no negatives. Very nice and simple. So there's some notation issues. So the elements of a sequence denoted by we usually use lowercase letters and with subscripts. So A1, A2, A3, A4, and so forth. Where usually the 1, 2, 3, and 4, those are the values of your variable. Those are the natural numbers. In general, the sequence itself, we usually use this notation, A sub n. Equals, sometimes it's equal some expression, sometimes it's just written like that. So for example, I can say that, let's say, sequence A sub n is defined by something like this, 1 over n. Okay, so the elements of this sequence would be, so then you assume that n is just a set of natural numbers, so 1, 2, 3, 4, 5. So the elements there are 1, 1/2, 1/3, 1/4, and so forth. Okay? So again, there's not much difference between when you play with functions and when you play with sequence as far as what you get. You have a independent variable, in this case it's m, which is a natural number, then you have a dependent variable that depending on, well, how we define a sequence. Sometimes we have a nice definition of a sequence, sometimes we just have a pile of numbers. It's a set of numbers. Is that okay? You got that from the video? So I don't know if you need me to do the examples. Are there any questions? Because this is from that video. I don't know if I'm repeating myself now. Were there any questions from that video? Or do you want me to just continue? Continue? I don't know. I mean, we're going to make it very short. So here's an example of a sequence. Let's call it b sub n, and it is defined as n over 1 minus 2n. And when we play with sequences, we're going to talk about the limit of a sequence. So the limit is always going to be as n goes to infinity. Okay, we're not going to ask about the limits as n approaches 5, because then it's just that. It's just the value of the sequence at 5. There's no way to approach 5 continuously. You go 1, 2, 3, 4, 5. There's nothing in between 4 and 5. So the only meaningful question is, does the limit as n goes to infinity exist? So we're going to talk about whether the sequence converges, if that limit exists and equals a real number, or diverges, meaning that it goes to infinity or just jumps between stuff. So let's play with this sequence. Can we figure out few elements? B1, B2, B3, B4. So yeah, for the first one, n equals 1, so we'll plug in 1, so it's 1 over 1 minus 2 times 1, right? So it's 1 over negative 1. So that's negative 1. Yeah, on that one, so it's 2 over 1 minus 2 times 2. So it's 2 over negative 3. So yes, negative 2/3. Well, you're too good for me right now, but so what is it if you plug in 3? So negative 3/5. You plug in 4. Negative 4/7, and so forth. Is that okay? Graphically speaking, all we have here is a bunch of dots, really. And if I plot these points, you know, 1 is the independent, negative 1 is dependent, so I have this point right here, 1, negative 1. And then I have 2 and negative 2/3, so let's call it that point. And then I have 3 and negative 3/5, so let's call it that point. It's not doing what I want to do precisely, but it stays below negative 1/2, is that right? Well, what happens when I get to infinity? This world does not explode. That's just ludicrous. Here we go. Is that better? That's it. That's the graph of the sequence. There's nothing that connects these dots. These are just the dots. There's nothing in between the dots. Yeah, I lost interest in the graph already. You got the idea what I was trying to do. Now, there are many ways for us to study this sequence. Because you see, like, we can try and apply. Because again, I'm going to ask you, can we figure out the limit of this sequence? Again, I'm not even bothering to write n approaches infinity. That's just implied here. There's no other limit that's even considered as n goes to infinity. Because if I try this, I mean, if I try this, how would we go about taking a limit like that? Divide all the terms by n, that's one way to go. If I go 1 over n, 1 over n, so that is the limit. Again, n goes to infinity. I mean, I'll write it here. So it's 1 over n minus 2. Well, that's an excellent point. We're gonna repeat that in a minute. What happens to 1 over n? So it goes to 0. So it looks like negative 1/2. So the question was, can we just use L'Hopital? Was that right? Did I hear it right? So the simple answer to that question is no. Because this is not really a continuous function in terms of the way we understand functions. Because in order for me to use L'Hopital, I have to take a derivative. In order for me to take a derivative, I expect function to be differentiable. Does differentiability implies continuity? Yes. Well, I'm in a bit of a pickle here because I'm going to try to take a derivative of that. That's not feasible. Does that make sense? But there is a workaround, as you're saying in this case, because I can actually think about a function of a regular continuous function that goes through these points. right? Can I find a function, some other mathematical creature that will do that? That matches the function at every, that matches our sequence at every natural number. Yeah, I can just say, well, why don't I consider this function? Now it's, it has some discontinuity issues, but it is continuous at all natural numbers. And it equals my b sub n for, x equals n, where n is a natural number, right? So I can actually study the behavior of this function, and it will tell me the behavior of that sequence. So I can use L'Hopital on this function, really, because now it's a nice and differentiable thing. Does that make sense? So the limit of this sequence, is the same as the limit as x approaches infinity of this function. And that function I can do, I can still divide everything by x. I can apply L'Hopital and so forth. Does that make sense? So eventually we're just going to say, well, derivative of n is 1 and derivative of negative 2n is negative 2 if necessary. Okay? But there are some technicalities. We can't just say, let's just start taking derivative of that thing that's defined by many, many little dots. Because, it's not differentiable at any point. But we can study a function that overlaps that sequence and makes it happy. Does that make sense? Go ahead. Yeah, we're not worried about it. Well, then, that specific sequence is just undefined at that natural number. So that's why it's not just defined on this set of natural numbers, it's just defined on some set of natural numbers. So yeah, you can have, if I have something like 1 over n minus 2, right? So it's undefined at 2, but I can still talk about what happens as n goes to infinity. That's going to be our major concern. Can we figure out, just looking at the sequence, whether it converges or not? So it's equivalent to finding horizontal asymptotes of functions, because that's what it is, right? Horizontal asymptote is what happens to a function as the variable goes to infinity. Is that okay? So, so definition of a limit, and again, the limit law is going to be very similar. So limit of a sequence. So a definition, so let L be a real number. So the limit of a sequence limit of a sequence a sub n is L if for, and this is your favorite, for every epsilon, oh, that's a 3. For every epsilon greater than 0, there exists n large enough, natural number n, so that the distance from a point on the sequence and a sub big N is within epsilon for all little n's greater than or equal to big N. Yeah. The big N plays the role, because you've seen the, write that thing down, I'll talk about it. It's a little messy. Because you remember your epsilon kind of limit thing from calc 1, right? You had epsilon delta definition, because you were talking about the limits as x was approaching some number on the number line, right? It wasn't going to infinity. You also had similar infinite definition. I don't know if Steve talked about that. But you had the idea, right? You know, you get within delta from a on the x, and then you land within epsilon on the y, okay? Well, here you just have to travel far enough on the x. That's what this big N is. You travel far enough on those little points, and then for every point past that, you're always going to be within some epsilon from whatever you believe the limit is. So graphically speaking, you know, let's say here is L, right? So here's that whatever I think the limit is. So then my sequence just does whatever crappy thing, you know, just jumps all over the place. But then at some point, you know, we just kind of around that L, maybe up, below, above L, below L, that doesn't matter. But whatever you think that epsilon is, you know, this is L minus epsilon, this is L plus epsilon, so you have this little window, then past a certain value N, everything past that will land within that little window, okay? And whatever your epsilon is, so if you shrink your epsilon, well, you just travel a little further. That's your N. Everything past that lands within epsilon from wherever your limit is. That's the definition of a limit of a sequence. Does that make sense? It's almost identical to the definition of an infinite limit. In calc 1, you had the limit of x as x approaches infinity equals 5. Is, you know, you travel far enough on the x-axis and you just land within whatever epsilon you think of from 5. Is that okay? We're not going to do anything else with that definition. We're not going to be doing any proofs using epsilons. It's just the more precise definition to get an idea of what's going on. I might have to prove a theorem or two while I'll invoke the definition, and we'll mess with that a little bit. But that's just if I feel good. Okay? But does that make sense, what the definition is? Now, the limit laws are identical as in calc 1. Let's say limit of Bn equals L and limit of An equals M. Then you have the following. The limit of An plus Bn is the same as limit of An plus the limit of Bn, so that's L plus M. So just like in calc 1, provided that those two sequences converge already, we can do that. You know, the constant multiple, if you have a limit k times An, so it's k times the limit of a sub n, so that's k times m in this case. And so forth. I'm not going to list them all. I mean, you have same limits, same limit laws as in calc 1. So if the two limit exists, so the product splits up, sum and differences split up, the quotients split up, and so forth. So I'm not going to list them all. They're all similar. And so forth. Same as in calc 1. So let's do a few examples. And again, we're just going to talk about whether something converges or not. So here's one sequence that is defined by 3 plus -1 to the power n. So does the limit exist? No, right? What are the elements of this sequence if I actually list them? So when n is 1, you subtract. When n is 2, you add. When n is 3, you subtract. When n is 4, you add. So every time n is odd, you subtract 1. Every time n is even, you add 1, right? So it's going to be 2, 4, 2, 4, 2, 4, and blah, 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 right? So is there a limit? No, for every epsilon. So no, right? Yeah, so no, because it has to work for whatever epsilon you think of. Okay, so no limit. It jumps between 2 and 4. So no limit. Another example, a sub n is defined by n squared over 2 to the n minus 1. So is there a limit? Yes, right? And what do you think that limit is? Yeah. Because we can actually invoke everything we talked about prior we went insane. We realize you have a numerator that's kind of a polynomial-ish, and you have a denominator that's exponential, right? And what is the exponential going to do to a polynomial? You're going to beat it badly, right? So at some point, the ratio is small. Both positive, right? Your numerator is positive, denominator is positive. Which doesn't matter in this case all that much, but in some cases it's also important to notice that. But we realize that you have a polynomial over exponential, so the limit should be 0. But in order to prove it, we can probably do that trick. When we replace this with a function, and only figure out the limit of a function, maybe use L'Hopital or whatever, okay? So we'll consider a function, which is x squared over 2 to the x minus 1. And we'll try to take the limit as x goes to infinity of x squared over 2 to the x minus 1. So how are we going to do that with some mathematical precision? Use L'Hopital, right? Because there's nothing I can do algebraically, because clearly this is infinity over infinity case. So I can go ahead and take the derivative of the top, so that's easy. And then, of course, you all remember how to take the derivative of a general exponential function. What's the derivative of 2 to the x? Two, right. Very good. So it's same thing times natural log of the base, which is consistent with your e to the x, right? E to the x is e to the x times natural log of e, which is 1, so it's still e to the x. So anyways, so what is this? What? Do it again? Let's do it again. So it's 2 over 2 to the x times ln of 2 squared. Right? So now your numerator is fixed, your denominator is still exponential, so that goes to 0. Right? So therefore, the limit of our sequence is also 0. Because this function matches the sequence on all the points that matter. How's that? Yeah, that's basically all we did in the video. That didn't take me 45 minutes. Who actually managed to watch the whole thing? Was I going off on a lot of weird tangents there?
It's just hard because like sometimes you start talking and you weren't writing anything, so it's like, are you writing it down or not?
And I edited that thing because at the end I really loved the last half an hour I was just drawing spheres on the board. Yeah, I got into 0 factorial and somebody asked me something and I started talking about the Riemann spheres and it was fun. But yeah, when you talk about the factorial, the notion of a factorial, it will show up a lot in chapter 9. Now, some of you have seen the factorials. I'm making it official. You know, the definition of n factorial, where n is what? No, because it could be 0, so it's not negative. N is not negative. Integer, but not negative. See, that's the problem, because 0, because we do define 0 factorial as well. So it's non-negative integer. How's that? Whole number. No, that's not right. Non-negative integer. Where n belongs to this crap. let's do this. N belongs to naturals union 0. Oh yeah, that's fancy. Yes, that's what N is. Could be 0. But the definition of N factorial is the product of all consecutive integers from 1 through N. Okay, so that's a product of 1 times 2 times 3 times all the way to N minus 2, N minus 1, N. So it's a product of consecutive natural numbers from 1 through N. So for example, 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. Whatever that is. What is that? 720. Okay. So 1 factorial is 1, but we also define 0 factorial is as 1. And that's a little weird. You just have to take it for now. Oh, damn it. See, I'm about to lose 30 minutes of lecture right now. But, well, first of all, it just makes a whole lot of math work out smoothly. So we're actually very happy that 0 factorial equals 1. You can just take it as a definition, but there is also the famous gamma function. I'm not going to talk about it, okay, because I'm going to start drawing spheres. Just definition. Let's just take it. By definition, to make math happy. Oh, shut up. By definition. Oh, it can't prove it. It's just, they define it first, and then all of a sudden they're like, oh, look at this weird thing that happened to spit out factorials for whatever reason. Actually, when you plug in 0, it spits out 1. But I'm not going to talk about that. But well, let me do one example that's off topic, because that will show up. You might have heard about the binomial theorem and binomial coefficients. Now, they help us to count things, and you see the binomial coefficients when we do expansions of sorts, like if I go a plus b cubed. If I expand that, that's a cubed plus 3a squared b plus 3ab squared plus what? B cubed. Okay? So what that means, if I take 3a's, right? If I take 3a's, I'm holding 3a's, and I try to put them in order, how many ways can I write 3a's? Really? How can you tell the difference between 3a and 3a's? Are they going to look the same to you? Well, I'm going to close my eyes. You will rearrange the a's, and I look back, and it just all look the same to me. So there's one way. But if I take 2 a's and 1 b, how many ways can I rearrange those? 3. BAA, ABA, AAB, right? So that's that kind of a 3. That's why you have those coefficients, really, because if you start expanding it without combining like terms, you will end up with ABA and AAB and BAA somewhere down the road. Same thing here. If I take 2 B's and 1 A and I'll try to rearrange them, I'll get 3 options. And if I just have 3 B's, there's only one way to list it, right? So that means if I take the same logic, and if I want to do a plus b to the power 7, so that means I'll have a to the 7th, a to the 6th b, a to the 5 b squared, a to the 4th b cubed, a cubed b to the 4th, a squared b to the 5th, oh boy, a b to the 6th, and then b to the 7th. Right? I'm just missing the coefficients. So a to the 7, that's easy. How many ways can I rearrange 7a's? There's only one, just 7a's. If I do a to the 6b, so 6a's, 1b, so they're just placing b, right? I can put B in the first place, second place, so forth. So I'll have 7 of those, right? But going further, how many ways can I rearrange 5 A's and 2 B's? I don't know. What? So there's a formula that does it for us. And the formula, here's the notation actually. 7, 2, like that. It's pronounced as 7 choose 2. So you have 7 objects, 2 of them are different. So you have 5 and 2. Okay? And the formula that does that, well, the general formula for n choose k is n factorial over k factorial times n minus k factorial. And we can derive that formula. It's a little, I'm by the way teaching probability right now for whatever reason. But if I apply this formula here, so I'll get 7 factorial, because it's still valid knowledge for you because you're going to learn how to simplify factorials. It's important. So it's 7 factorial, then 2 factorial, and n minus k, so 7 minus 2, so it's 5 factorial. Okay, so it's really the total in the numerator and then the 2 options, 2 and a 5 in the denominator. Now we can reduce that, because what is 7 factorial? It is 7 times 6 times 5, 4, 3, 2. So I can actually think of 7 factorial as 7 times 6 times 5 factorial. Right? So 5 factorials will cancel. So it's 7 times 6 times 5 factorial over 2 factorial is 2, 5 factorial is 5 factorial, so they cancel. So 2 goes into 6 3 times, so 21. So 21 goes here. So there are 21 options for that. Okay? I'll do the same, let's say, for that one. 7, 3. So it'll be 7 factorial, 3 factorial, 4 factorial. So 7 is 7 times 6 times 5 times 4 factorial, while 3 factorial equals 6, and the 4 factorial cancels, 6 is canceled, so you get 35. So this is 35 here. So there are 35 ways to rearrange 3 B's and 4 A's. Okay? Now the rest would be the symmetry. This is also 35. This is also 21, and that's 7. Okay? But does that make sense why it was 7 for 6 B's and 1 A? I mean, we don't need mathematical formula to come up with that answer, right? I mean, it's just, you have 6 A's, and then you just put B up front, and then you put B in the second place and the third place, so there's 7 options. And same thing for B to the power 7. There's only one way to list 7 B's. It's just 7 B's. Right? We're happy with those 2 coefficients, right? Now let me show you. If I do, let's say 6 and 1, if I compute this formula, 7 choose 1, so that becomes 7 factorial over 1 factorial times 6 factorial. It will equal 7, because 7 factorial is 7 times 6 factorial. 1 is 1, who cares? That's 6 factorials, they cancel, that equals 7. As expected, right? But for the very first one, the coefficient is 1, right? How many B's do I have there? 0. So that's really 7 choose 0. And if I apply that formula, I'll get 7 factorial over 0 factorial times 7 factorial, right? Our gut feeling tells us the answer is 1. Right? Isn't that convenient that we define 0 factorial to be 1 then, all of a sudden? Yes, so it's kind of helps us to make those computations go a whole lot easier. Makes our, things that kind of make sense work out. But it's, you just take it as a definition. Sorry. But no, I don't talk about it. Okay, so good. Well, that's the easy way to do computations. Okay, you can, your calculator possesses a factorial button. Your calculator actually possesses this button. Does anybody have a basic scientific calculator? Not the graphing one, but just. Let me see. It should, yeah. I have no idea how to use a calculator, but let me point out. Scary. Wow, that's some zoom going on in here. On his calculator, this button right here, the one that has factorial, and then NCR, this is literally means N choose R. So, well, I wrote N choose K. So, let's see if we can make that. What the hell were you computing before? Well, it's permutations. So that's where we actually, if I can actually distinguish between the A's. So C for combinations, P for permutations. So it's if order actually matters. Like this. Okay, how many students I have in class? 14, okay? I'm going to say, I'm just going to issue 3 A's randomly. So I'm going to grab 3 students out of the hat. So 3 randomly out of 14, so that's N choose 14. I don't care who comes first, who comes second, who comes third. But what if I say I'm going to grab 3 students and then go A, B, C among those 3? So then the order in which I grab you matters. So that's permutation. But anyways. Okay, so let's try. Well, let me, okay, you don't see the, okay, I see what you mean. Yeah, I know. So I was just testing. So yeah, look at this. If I go 7, choose 3. What did we get by our, we got 21, 35. And if I hit that, it just gives me 35. So, I mean, your calculator has those formulas built in, but you can compute it by just going, 7 factorial, where is it? Divided by maybe 6 factorial, without realizing that the answer should be 7. But, So yeah, your calculator has those. So when you take your probability course, those buttons, because you will take your probability course at some point, aren't you? Some kind of a statistics engineering probability class. Because in probability, it's really important for us how to count. And there's going to be another application of integration in that class. But you do need Calc 3 style integrals to take probability. Anyway, so I still went off a little bit. What? No, you need double integrals. Because you're going to be, because your probability density functions will most likely have multiple variables. So you're going to talk about the. Okay, good. All right, so let's talk about. All right, so that was nice and fun when you can kind of relate it to Calc 1. Sometimes there are other ways to show whether something converges. So first, let's define a notion of increasing sequence. What do you think that means? Just by the way it sounds. It's going up. So that means if I take 2 elements in the sequence, a n plus 1, so that's the next from a sub n. Which one is bigger? N plus 1, that's the next one, right? This is n equals 5, this is n equals 6, so that's the next one. So it should be facing that way, right? So that's increasing, that's going up. Now, if it's like that, it doesn't affect the purpose of why we bother defining an increasing sequence. So really, increasing sequence, in other words, is a non-decreasing sequence. And I know you love the. Can you taste the difference between increasing sequence and non-decreasing sequence? Yeah. Well, do you understand what the big difference is? Because if it's a strict inequality, then it's just increasing. But if it's greater than or equal to at each step, well, then it's not quite increasing, but it's definitely non-decreasing. So well, yeah, well, none. Yeah, so that means it's a constant. That's the implication of that. So it's a constant, right? It's a constant sequence. Those are easy to deal with, right? The limit of a constant sequence is that constant. So, but again, basically what I'm going to get at, this is what's going to happen in a little future. I'm going to tell you that, let's say you have a sequence that's always going up, or at least it's never coming down. It's going up, maybe it stays flat, it goes up, stays flat, but at least it's moving in a general upward direction. So think about this. So each point gets a little higher, a little higher, a little higher. Okay, increasing sequence. But at the same time, I'll tell you that there is some magic number that sequence will never get past. So there is some kind of a bound that the sequence never gets through. Doesn't matter what it is. Could be 5, could be 5 and 12. Because I mean, if your sequence can never get past 5, it will not get past 12. So you're going to have many of those bounds. Doesn't matter which one you look at. But so if your sequence generally is going up, but never passes some value, but keep going up, but never passes a value, but keeps going up, but never passes a value, that's a convergent sequence. Because eventually it will start flattening out at some point. Not necessarily the value that I had in mind. Could be a lower value, but it will eventually flatten out. So it will converge. So we call those bounded monotonic sequences. Monotonic means it's non-decreasing. Or non-increasing if you have a sequence that's always kind of going down and it has a very small number that never passes, then it will converge to some number on that side. Does that make sense? I mean, we can make an epsilon proof of that statement. It's a little messy. Monotonic, yeah. But I'll write it down, don't worry about it. I was just giving I know this is what you were talking about that I was talking a lot. But anyway, so, and then at the same time we can do the decreasing sequence. Or in other words, non-increasing. So that means the next step is less than or equal to the one before. Okay? And I mean, I think your book, if I remember it correctly, is being very strict. It'll just say increasing sequence, an plus 1 is greater than n for all n. Or an plus 1 is less than a sub n for all n. I don't care about all n, but I'll say for some n's that are greater than, at some point it starts increasing or decreasing. I mean, if you get a sequence that does, it just does whatever, but then at some point it just starts just going up and up and up like that at some point it becomes an increasing sequence. That's really what we worry about. Okay, just like when taking limits, infinite limits, it doesn't matter what happens when x equals 12. Who cares? All matters what happens as x increases. So maybe at some point your sequence is pretty chaotic, but then it just starts going up and up and up, and then it will never pass some number here. So it will eventually converge to something, right? It's not coming down, because if it was going up and down, then I cannot say anything. But it's always going up, and it's flattening out because there is a bound on the top. Okay? So for our purposes, it's at some point it has to be, and I meant that was going up, not down. Okay? So if a sequence is increasing or decreasing, we call those monotonic sequences. So another definition, upper bound. So if a sub n is less than or equal to some number m, then we say that M is an upper bound for a sequence. For all M. So a sequence never, the values of a sequence never get past a certain number. So upper bound, same notion, we can have a lower bound. So if a sub n is greater than or equal to some, let's call it little m, then we say that little m is a lower bound of a sequence. For all. So if a sequence has an upper bound and a lower bound, then we'll say that the sequence is bounded. So bounded sequence, from above, from below. So you have a bounded sequence that's also monotonic, either going up or going down, and it's bounded. It will converge. Okay? You can also say you have an increasing sequence bounded above, that will converge. You have a decreasing sequence bounded below, that will converge. Okay? So you need to have a bound in the direction of increase or decrease. Does that make sense? Because it will have to flatten out eventually. So a bounded, so if a sequence is bounded and monotonic, then it converges. Yes? Yeah. Yeah, that will diverge. Yeah, that's for sure. But I mean, that sequence, what was it? This one, right? I mean, we can actually talk about whether it's increasing or decreasing sequence. Okay? And if we can prove, like, I mean, this one, we can actually compute the limit and blah, blah, blah. But let's say we didn't possess the L'Hopital or whatever. The question was, is this convergent sequence? So if you're actually able to show that this sequence, let's say, decreases at each additional step, and so if it's a decreasing sequence, then if you can actually show that it's bounded from below, that there is a number that that sequence never gets to, then it's convergent. Now, what it converges to, that's a different story. It will only tell whether it converges, because then we have to understand, let's say, what I mentioned earlier, if I can prove that this sequence is bounded below by -1, that means it's bounded below by -2 and -5. You have infinitely many bounds. Does that make sense? Because, I mean, if it never gets below -1, it will definitely never get below -5. Well, very good question. Because among those infinitely many lower bounds, there is the highest among them all. There is the highest number for which I can start playing epsilon game. And that highest number will actually be the limit of that sequence. So and I know the verbiage is going to sound weird, but I actually have the largest lower bound and the least upper bound. Among all the upper bounds, there is the smallest one, and this will be the value of the limit. Okay, now finding those lowest upper bounds or the greatest lower bounds, that's a different story. I don't know, the verbiage is weird, and you will all take fun math courses where the whole class will be, hey, let's consider the, the least upper bound. The name of that is actually the supremum of the set. There's a set bounded from above, there is the lowest bound of them all. So those bounds will be the actual limits. We have an axiom of real numbers called the completeness axiom. Because, between any two real numbers, there is another real number. That's basically the axiom, which implies that among all those upper bounds, there is the least upper bound, and among all the lower bounds, there is the greatest upper bound. That's, you shouldn't be writing. This is me talking, okay? But for our purposes, just to say whether this is convergent, I can say, well, it's bounded below by -7. The way I prove that, I set it equal to -7, and I show, well, it's always greater than -7, regardless of the value of the variable a. So it's bounded below by -7. And then I can show that it's a decreasing sequence. That's a different story. How do you show that something is decreasing? How do you show that something is decreasing? I mean, there are many ways. There's one way that should show up really fast. No. You cannot do that. You cannot plug in all the numbers. Well, that's not enough. What if there is a some number down there? Well, if a derivative of a function is negative, then the function is decreasing, right? And if the derivative of a function is positive, then the function is increasing, right? Now, this function is probably increasing. So I need to show that it's bounded from above and increasing, and then it's convergent. Well, I mean, we were playing with the... Is it decreasing? Yeah, but right, but I'm talking about the... Right. How do you show that it's decreasing? Anyways, what? Right. Oh, yeah, never mind. Yeah, we're good. Yeah. Let me talk about it for a second. So, yeah, if I go back to this sequence, yeah, it's decreasing. I don't know what the hell it's doing. N squared over 2 to the n minus 1. So, let's show that it's bounded first, right? So we think it's decreasing, so we need to show that it's bounded from below. So think about a number that you think this sequence will never get to. Well, 0 is tough. -1, right? Well, n squared over 2n minus 1. Do you agree that that thing... Well, actually, we can show that it's 0. I mean, n squared is positive. 2n minus 1 is positive for natural n's, right? For n greater than or equal to 1, n squared stays positive, and 2 to the power n minus 1 stays positive. Do you agree with that? So therefore, n squared over 2n minus 1 is greater than or equal to 0. I mean, for all n, really. Well, no. For n greater than or equal to 1, right? So actually, it's bounded by 0. I can say it's bounded by 0. It's also bounded by -3 if it's bounded by 0. Yeah, we'll have the square. Yeah. So anyway, so it's bounded below. Now, to show that it's decreasing or increasing, yes, take the derivative. So f of x equals x squared over 2 to the x minus 1. So let's take a derivative of that. So what's the derivative of that? So it's 2x minus 1 squared. I have to use the quotient rule now. So it's 2x times 2x minus 1 minus x squared times 2x times the ln of 2, right? So I have to show that numerator is negative, right? If the numerator is negative, then we're golden, because the denominator is positive. So let's mess with that numerator. What is this? It's 2x times 2 to the x minus 2x. Oh, I don't know how to show whether that's negative. Wasn't it? No, it was. Yeah, right there. Yeah, you think about the other one. So look at that numerator. What can we say? We can, what is that? That's nasty. What can I do some factoring and pull out an x? What's left if I pull out an x? It's 2 to the x plus 1, right? Minus 2 minus x times 2 to the x times the ln of 2, right? Why is this thing negative? That, yeah, because I mean, for x is greater, because all it is, it's 2 times 2 to the x. This is x times 2 to the x. So when x, all I have to do is just for x, when x is 2, then it's already, this is already greater than that. So you're going to get a negative minus another 2. So yeah. Well, plug it in, you'll get a negative number, right? If x equals 1, when x equals 1, you'll get 4, right? Minus 2 minus 2 times natural log of 2. So 2 and 2 ln of 2 is bigger than 4. So that's less than 0. You go, and so it will be the rest, right? So that's negative. So the derivative is negative, then the function is decreasing. So that's a decreasing sequence, right? Since the derivative is negative, so then the function is decreasing on that interval. So the sequence is decreasing. You got a decreasing sequence that's bounded below, so it's convergent. Now what it converges to, that doesn't tell us. Okay? I mean, we'll have to run a separate proof to show that 0 is in fact the greatest lower bound of them all. Isn't that fun? This is fun. It's called mathematical analysis. That's what we're doing right now. We're messing with, I mean, we really, that's what things get hard when we make things simple. I mean, we only, think about this. We just dropped everything we know about functions. We just focus on things that only take in natural numbers. It's really basic. And then things get a little ugly. All right. So let's try this one. There's a fun example. A sub n is defined by sine of square root of n over n. What do you think? 0, right? Because I mean, ignoring everything that's inside the sign, it's between -1 and 1, right? Your numerator is between -1 and 1. Ignoring, I'm not even looking what's inside the sign. Because there's actually, it's going to play a little bit of extra role. But sign is between -1 and 1, and the denominator keeps growing, right? So you're going to be jumping, positive, negative, positive, negative, positive, positive, negative, negative. You're going to have points above 0, below 0, but they'll just get closer and closer to 0 as n gets big. Does that make sense? If I just have a sign in there, I'm ignoring that it's a square root and n is strictly positive, so that numerator will just be positive, right? Because the sign of a positive number, yeah, not really, you're right, not really. I have to be careful. Yeah, if I did like 1 over square root of n, then yes. Yeah, it'll be negative. So let me take it back. But so still, it doesn't even matter in this case, okay? Because the numerator is still between -1 and 1, just ignoring everything on the inside. Sometimes you're going to have the inside that will make sure that everything comes out positive or whatever. But it doesn't matter in this case. So if we say that, then whatever it is I was talking about, that is, monotonic or bounded, it won't work, because I won't be able to prove that it's monotonic, right? Because it's not. Because you're saying it could be positive, it could be negative. So I cannot have few positive and then few negative and then few positive. So it's neither increasing nor decreasing or whatever, okay? So, but are there any other ways for us to take the limit of this squeeze? We can do some squeezing, right? Because every time you have those periodic things, it's always going to be between that and that, right? Whatever that square root of n, in this case, is just irrelevant, really. It doesn't do anything for us. Because what do you know? That goes to 0, and that goes to 0. So by the squeeze theorem, the limit of our sequence is 0. So we don't have to do anything else there. So we can do the squeezing. And squeezing is always nice when your numerator, at least your numerator is bound. Your denominator explodes. Then the squeeze will work out. What is this? How about this example? So just determine whether a sequence converges or diverges. And the sequences, let's try this one. 1 plus -1 to the power n over n. What do you think about this one? Zero, right? Because what happens to your numerator? It's 0, 2, 0, 2, 0, 2, 0, 2, right? And your denominator is 1, 2, 3, 4, 5. So we can do the squeeze thing again. Because this sequence is always less than or equal to 2 over n and greater than or equal to 0 over n, which is 0, right? That's identically 0. That's going to 0. So by the squeeze theorem, you get yourself a 0. So the squeeze theorem, you gotta love it. Is 0. That makes sense? So every time, even though, again, if the question was just the numerator, then yeah, that thing diverges. It's 0, 2, 0, 2, 0, 2, that diverges. But since your numerator is kind of bounded, now with having a denominator that's growing, the thing will go to 0. So that should, trigger the squeeze theorem response. How about this example? I think it was so the sequence is n minus 2 factorial over n factorial. What do you think will happen there? 0. Yes. Why? Yes, so we'll reduce it. We'll use our knowledge of factorial. So, because how do you get to n factorial? You have to multiply first n minus 2 terms times the next, which is n minus 1, times the next, which is n. So n factorial can be expressed as n minus 2 factorial times n minus 1 times n, right? Let's say if n is 7. Then n minus 2 is 5, so it's 5 factorial, and 7 factorial is the same as 5 factorial times 6 times 7. So these two cancel, so then you just get something nice and simple, n minus 1 times n, and that's good. That goes to 0, right? So therefore, the limit of this sequence is 0. All right, so let me give you a few more. What? No, there's, um, I mean, the notable application will happen like at the end of chapter 9. We're just developing a little tools we'll need. I mean, we won't be actually, you might just get like a 1 or 2, does this sequence converge questions, on the exams and the finals, because that's just a little minor afterthought in the big scheme of what we're about to start doing here. But the concept of a sequence will show up in many little places in the realm of bigger application. But yeah, we'll apply this. So anyway, so how to determine whether sequence is convergent? So I'm going to give you a few sequence converges or diverges. So one, make it a calc 1-ish problem. So for example, if I have a sequence natural log of n squared over n, we can probably take a wild guess. What do you think? 0, right? You have a log which is slow over linear which is faster, so it should be 0. Now, how would we prove that? L'Hopital. So that's what I mean making calc 1-ish. Make it into a normal function and then pretend that calc 1 should cover L'Hopital, and then it makes it calc 1-ish. So consider f of x is natural log of x squared over x, which you can totally write as 2 natural logs of x over x to make it a little easier. So then limit as x goes to infinity of this function is infinity over infinity form, so we can apply the L'Hopital's rule. So it's a 1 in the denominator and it's 2 over x in the numerator, right? So what is that? That's 0, right? It's 2 over x that goes to infinity, so that equals 0. So therefore, the limit of our sequence is also 0. So make it calc 1-ish. Another, we can use the squeeze theorem when applicable. Here I have an example of cosine of pi over 2n plus 1 over n squared. So the numerator is between -1 and 1, right? So then our sequence is between 1 over n squared and negative 1 over n squared, regardless of what's inside that cosine, really. So this goes to 0, that goes to 0. So therefore, the limit of our sequence, let's call it a sub n, equals 0 by the squeeze theorem. Yeah, I'm about to show you one. How about this example? Well, actually, I'll take it back. It still equals 0. No, it's not always 0. But let's try this one where you get a sequence that's well, how would we make an argument here? What? No, that's not a calc argument. That's just an argument that I'm not sure. Well, we need a little more precision. Well, prove that. That's the... I know it's very close to 0. Well, let's put some precision on this. Conjugate. Who said that? Very good. Let's conjugate this thing. Because if I do the conjugate, if I do square root of n plus 2 minus square root of n, and I'll multiply it by square root of n plus 2 plus square root of n minus square root of n plus 2 plus the square root of n. Because now we're putting a plus in the denominator, which we don't need to argue. That goes to infinity, right? While in the numerator, it's just difference of squares, so that's n plus 2 minus n over that. And those two cancel, so that's 2 over plus the square root of n. So we see that's good, right? So numerator is 2, denominator is big, so the whole thing goes to 0. Right? Can we make a bounded monotonic argument here? I mean, we won't get 0, but we'll get convergence. That thing is positive, right? I mean, that we don't need to prove. Square root of n plus 2 is greater than square root of n, so the thing remains greater than 0. So it's bounded, right? I just need to show that it's decreasing, right? Can we show that it's decreasing? You can try with the derivative. And again, I'm just playing right now, so you can say the monotonic bounded approach. So since square root of n plus 2 is greater than square root of n, we know that square root of n plus 2 minus square root of n is greater than 0, greater than or equal to 0, whatever, right? It stays positive, not negative, 0. So it's bounded by 0, it's bounded by negative 5, all that I care. It's bounded, right? Bounded from below. So therefore, from below. Now 2, to show that it's decreasing, we can take the derivative. We can consider this function, take the derivative, So what would that be? It's 1 over 2 square roots of x plus 2 minus 1 over 2 square roots of x. Right? That would be the derivative. Now, again, we don't need to argue that the first denominator is bigger than the second denominator, because that's plus 2. Right? So that makes the first fraction smaller than the second fraction. You agree with that? Therefore, it's negative. So it's less than 0 for x is greater than or equal to 1, and that's all we really care. So therefore, f is a decreasing function. So therefore, the sequence is decreasing and bounded below. So therefore, converges. But I don't know what it converges to. I mean, we know it's 0 by doing the previous work. But this at least it gives us the convergence, but we don't know what it converges to. Okay? All right. I'll stop. We're not done talking about this. We'll finish sequences on Friday. Do no homework yet.